All right, here's 2-1 day one. Really two topics, three I should say, kind of two. We are getting into distributions, okay? Which if you need to go back to chapter 4 in your book and check out that definition, do it. It's a description, a distribution that is, a description of the outcomes a variable can take on and how often it takes them. Okay, here we have a distribution of test scores from some set of chapter 1 statistics exams from once upon a time. I don't remember when. Okay, maybe 3 or 4 years ago. So it tells us that here the possible range for scores was from 65 to 100. Like you could have gotten less, but nobody did. So all our possible outcomes are between 65 and 100. But notice, not all scores happen with the same frequency. There's a lot more scores in the 70s, 80s, and 90s than at the 100 level or in the 60s. Okay? So this stem plot does tell us, notice it has a key because I put the scores in percents. It tells us what outcomes we could expect and then how often they happened. Those are the two things that distribution does. All right, so within that, the three things we're looking at today is how to describe location within a distribution, which would mean percentiles and z-scores are the most common way we do it. And the third thing is we're going to make a cumulative frequency table. All right? First things first, though, let's talk about percentiles. Here's how they're calculated. We have 23 pieces of data, so percentiles are always going to be out of 23. If you scored an 88, 11 people had a lower score than you did. Okay, this is how percentiles are calculated. Okay. That would give you 0.48. And we'd say it just like this, the 48th percentile. Now this means 48% of individuals that took the test scored below 88. It tells you kind of where you were at relative to everybody else. Okay, in the context of taking a test, the higher the percentile, the better you would feel about it, right? If you were up in like the 80th, 90th percentile, it means you scored higher than lots and lots and lots of individuals that took it. For 74, there's only three. 65, 68, and 70 are the only scores that are lower. That would be 0.13. So your score would be at the 13th percentile. And then a 91. There are 15 scores less than 91, which would put you at the 65th percentile. All right, on the next slide, we are going to make a cumulative relative frequency table. It's kind of like a scatter plot, but we connect the points. But here's what we do. It is a way of connecting a piece of data to its percentile. Okay, that's more or less what it does. We'll do two things with them. We'll make one, and then we'll go over how to read one. And realistically, it is a little bit more important that you can read it. But making it is good to kind of see where, kind of the logic behind how it's set up. All right, so I've got these intervals, 60 to 64. That had nobody. 65 to 69, and feel free to reference these to our stem plot that we made. There were two scores between 65 and 69. 2 from 70 to 74. 4, 1, 6, 4, and 4. Those should all add up to 23. Now when we say relative, we're just now saying back to the whole. 2 out of 23, 4 out of 23, 1, 6, 4, and 4. Now, cumulative means to add them up as we go. All right? So for 60 to 64, there was still nobody. 65 to 69, there were 2. 70 to 74, add on those 2 more, but we're keeping the 2 from before. Okay, so this now tells us there were 4 scores that were 74 or less. There were 8 scores that were 79 or less, 9 that were 84 or less, 15 that were 89 or less, 19 that were 94 or less. This will have to amend. We did have one perfect one. So there were 23, that's everybody, that were 100 or less. Okay? So now over here, if we did 0 out of 23, that means our percentile would be the 0th. If you were at 69, we'll go 2 out of 23, you would be at the 9th percentile. If your score was at 74, you would be at the 17th percentile. If you scored at 79, we would go 8 out of 23. You would be at the 34th. Nine out of 23 would be 39th. If you scored at 89, that would be 15 out of 23, which would be the 65th. 19 out of 23, that would be if your score was at 94, that would put you in the 82nd percentile. And if you were up at 100, and you were that perfect paper, you would be at the 100th. Everybody's score was below yours. All right, now we're going to keep track of all this data that we had, okay, in that table, especially the last column. So we had said down here, if we were at 64, we were at the 0th percentile. Okay, so I'm basically going to plot some points on a scatter plot. And the x-axis is the score on the test. The y-axis is your percentile. All right, so the second one we had was if you were at 69, you were at the 9th percentile, which would be about right there. If you were at the 74th, or if your score was 74, that would put you up at the 17th percentile. 79 would put you up at the 34th. 84 would put you at about the 39th. 89 would send you all the way up to the 65th. That was a big jump. '94 would send you to the 82nd. And up here, we'd go up to 100. And then I would go and connect all these dots. And we have a cumulative relative frequency table. Now let's go over how to read one. I'm going to switch the context on you and use a little bit nicer looking graph. Oh, it's got the lifetime of 200 watt bulbs. And it didn't put the units on here. I'm going to assume it's in hours. All right, so we could use this to estimate where is the 60th percentile. Well, that's right over here. This is how this works. Draw a line over, straight over, till you hit the graph, and then go straight down. And it looks to be about 1,000 hours. So if you've got a bulb that lasted for 1,000 hours, a 200 watt bulb, it was slightly better than average because the 50th percentile would be right in the middle. Okay? Let's use it to estimate the interquartile range. Mostly because I want to review what that is. Q3 minus Q1, right? And even after chapter 1, a lot of people don't realize the interquartile range is the 75th percentile minus the 25th. Okay, so if you were to say the 75th percentile, that's synonymous with Q3. It's the same thing as the third quartile. Same thing with Q1 and the 25th. Let's head back up here. This one's a little bit tougher to do. I'm going to say 75 is like right here. 25 is like right here. It's just an estimate. Oh, it's between 7 and 9, but it's closer to 900. I'm going to say 850. Between 900 and 1,000, between 900 and 1,100, a little bit closer to 1,100, I'm going to say 1,050. So Q3 was about 1,050. I thought Q1 was about 850. The interquartile range would be 200 hours, roughly. All right, moving on to our last topic for today, the lovely Z-score. Okay. First thing we have is the definition of how a Z-score is calculated. Okay. Important to understand here, wherever you see X, that always refers to just an individual piece of data from your set. Okay. We're going to go back to the test score example. Okay, we're going to go back to the test score. Now to do this, we need the mean and the standard deviation, which I went and calculated for you. The mean, or X bar as we call it, is 85, and the standard deviation for that set of data is about 9.98. Okay? So the average score was right around 85, but on average, the scores in the class varied by about 10 points from 85. Okay? Let's say you got a 91. Let's get your Z-score. A Z-score is a relatively simple calculation. Take away the mean, put it over the standard deviation, and you get 0.6. That's easy enough, but then what about this part of explaining what it means? Okay? All we did was change the units. Okay? All we did is change the units. After we have a Z-score, your units aren't, percentage points on a test anymore. They're now in standard deviations. Okay? This score is 0.6 standard deviations. It's a positive Z-score. So that means it was above the mean. Okay? The units change to standard deviations. It's kind of weird at first because you're like, standard deviations can be a unit, and it totally can. And it's actually one that we really like. Let's say you had gotten a 66. Take away 85. Divide by 9.98. This score, if you had gotten a 66, is 1.9 standard deviations below the mean. How do I know it's below the mean? Well, I got a negative Z-score. Negative Z-scores are always, they always mean that you have a piece of data that is below the mean. Okay? Positive Z-scores are above the mean. But then if you just look at the actual data itself, you're like, well, yeah, the mean was 85 and the score was 66. That's well below 85. And one more just for good measure. Once you calculate a lot of Z-scores, you start to be able to kind of anticipate what they're going to be. This one's going to be negative, but just barely. It's slightly below the mean. The score is 0.4 standard deviations below the mean. Okay? So much more to come with Z-scores. Okay? They're a huge thing for us. We'll use them all the time. All I want you thinking about right now is, one, for a piece of data, can I calculate a Z-score? And two, can I explain what that Z-score means?